Okay, welcome back, Physics 30s, to our next chapter, which is chapter 2, and in this chapter we're going to be looking at electrostatics. All matter is made up of atoms, and you've probably seen a diagram similar to this before in chemistry, where I show the protons and neutrons in the center nucleus, and then negative electrons orbiting around the outside. Now this may seem like pretty common knowledge, but I think the structure of an atom and that everything is made of these is one of the most interesting scientific facts. And that's because this diagram isn't even close to scale. Really, the nucleus is much smaller, and there's much more space between the nucleus and the electrons. The nucleus is incredibly small, but has pretty much all the mass of the atom. So it's super tiny, yet super heavy. And then in between the electrons and the nucleus is absolutely nothing. And this isn't just a small empty space. If we consider the nucleus to be the size of a basketball, the electrons would be kilometers away. So that's a lot of empty space. And remember, all mass is made of atoms. So if you're going to zoom in on anything to the atomic level, it's going to look like this. These very tiny, very heavy nuclei, a whole bunch of nothing, and then they're orbiting very light electrons. So there's a ton of empty space in that diagram. It's almost like everything is hollow. It's got all their mass and then a whole bunch of nothing before you get to the next nucleus. If we could get rid of all that space, what it would be like? Well, let's get rid of those and put all of these nuclei together, you would have an extremely small and extremely heavy mass. If you were to take just the size of a sugar cube and have it full of just nuclei, that would weigh 100 million tons on Earth. That's how heavy these nuclei are. And things like this actually exist. They're called neutron stars, and they have about the mass of about 1.5 times the mass of our sun, but it's all condensed into the sphere that's a diameter of about 20 kilometers. So I find it really interesting to think that you and all matter that you interact with looks like this. But anyway, the reason we want to talk about atoms is we're going to be talking about those pluses and minuses and the charges that exist within atoms in today's lesson. So even though the electrons are so much smaller than the protons, they have the same amount of charge. Electrons have a charge of negative 1.6 times 10 to the negative 19 coulombs, and protons have a charge of positive 1.6 times 10 to the negative 19 coulombs. We'll talk about measuring how much charge is going to be flowing and stuff later, but right now we just want to note that they're the same amount of charge. Electrons are minus, protons are plus. And in this chapter in electrostatics, we're going to be looking at the study of electrical charges collected and held in one place. So looking at positive and negatively charged things. Now, it is important to note that in the study of electrostatics, we're not going to be creating any new charge. We have the same amount of pluses and minuses. We're just going to be rearranging them into positively charged and negatively charged things. But we can't make any new charge. This is the law of conservation of charge, and basically just says that a net charge of an isolated system must be conserved. So we have a material with equal pluses and equal minuses. How we're going to create charges, we're simply going to move the electrons to a different place. So now we have positive charge over here and negative charge over there. But we still have the same amount of pluses and minuses, we've just separated them. Now some materials have it where the electrons are easier to move than others. In conductors, the electrons are free to move, but in insulators, electrons are bound to their nucleus. So if we look down at this rectangle over there, the gray one, say this is a metal. Metals are good conductors. The positives there are going to stay pretty much locked in place. Those part of the atoms are going to stay there, but the electrons are free to move. All the electrons are going to be able to move and flow around, and it's sometimes described as a sea of electrons, or like an ocean of electrons that can just flow and move rather easily. The electrons in an insulator are moving as well, but they're bound to the nucleus. They can be going around in an orbit around that nucleus, but they're not going to leave to be able to go to another one. So we're going to be looking at moving electrons in conductors, and it's good to note here that like charges repel and opposite charges attract. So two negatives will repel from each other, two positives will repel from each other, and a positive and negative will want to come together. So I like to think of this as electrons kind of with a personality, and they don't like to be around other electrons. So whenever they're in a space where there are other electrons, they're going to try to move as far apart from the other ones as they can. And when a positive nucleus is introduced or brought close to them, they like these, and they are going to move closer towards a positive charge as they like being near positives. So now let's take a look at these electrons in a conductor, and they're all kind of spread out because they don't want to be near each other. The charge is evenly spread out, but here we have equal pluses and equal minuses, so it's a neutral metal. But now we're going to bring some electrons and we're going to charge up this metal by bringing some electrons in. Those electrons aren't just going to stay in that clump. All of them are going to try to spread out and get away from each other as much as possible. So the charge is going to spread out evenly over that metal and they're all going to try and move away. Now if we bring a conductor up to that metal, it kind of acts as like an escape route where they're all trying to get away from each other, and now there's a place for 3 electrons to leave and it goes back to our original charge and they'll redistribute once again. This makes conductors good for building circuits because electricity is just the flow of electrons, and we want those electrons to be able to flow easily through a conductor. So the better conductor you have, the better electricity is going to flow through it. So now that we have those basics down, we're going to be looking at how to charge a material. And there's 3 ways of charging a material. There's charging by friction, charging by conduction, and charging by induction. So first, let's start with charging by friction. When 2 materials are rubbed against another, the electrons move from one material to another. This is very commonly shown with rubbing a balloon on someone's hair. The balloon and the person are both neutral to start because they have equal number of pluses and minuses. But then when we rub the balloon on the hair, electrons get transferred from the hair to the balloon. This makes it so that the balloon is negatively charged and the person's hair is positively charged. And then we get an effect like this where the hair seems to be attracted to the balloons. And that again isn't because we've made a charge, we've just separated charge. So there's all in that picture, if you want to count them up, same amount of pluses and minuses, but now the electrons have been pulled towards the balloons and there's more pluses remaining on the person. So that makes their hair positive, attracting to the negative balloons. The next way to charge something is by conduction. This is when electrons move to balance out charge when objects come into contact with one another. So let's say that we have this rubber rod and a piece of fur. This is a common way to build up charge, is we rub them together and build up charge by friction. The rubber rod is going to take the electrons kind of like the rubber balloon, and it's going to become negatively charged. And now we're going to get rid of the fur and we can transfer that negative charge to something else just by coming into contact with it. So I pull up this gold ball. So gold is a good conductor and can have moving electrons. So I take that gold ball and I touch it to this rubber rod now, and the electrons are free to move. Remember, they all want to get away from each other on that rod. And so now they're going to be able to move into the gold ball. And the gold ball initially was neutral. It had the same amount of plus and minus. But the electrons on the rod are going to again try to get away from each other, so they're going to go to where there's less minuses, which is going to be on the ball. So they're going to move in that direction until there's equal charge on both sides and the electrons are spread out as much as they can get away from each other. And now if we were going to remove the rubber rod from the ball, they would both have excess electrons and they would both have a negative charge. And lastly, we're going to look at charging by induction. These are usually the trickiest types of questions and the hardest one to understand. So we're going to use a lot of animations and analogies here to try and explain what induction is. And the 2 key things to remember are things that we've seen before, is that positives are going to stay in the same spot, only electrons are going to move, and electrons are going to move towards positively charged nuclei and away from other negatively charged electrons. So let's take a look at induction. Okay, so the first part is that electrons are going to move in the presence of a near charge. So what I mean by this is when we move objects close to one another, we're going to have a response from the electrons in those objects, even before they touch. When they touch, that's talking about conduction and movement there. This is when they come close together. So let's start with a metal sphere, and we have pluses and minuses on the sphere. This is neutral overall. And then we're going to take that negatively charged rod. Now we're going to move that negatively charged rod close to the sphere. So now we're bringing negatives close to the neutral sphere. Remember, the protons can't move in that sphere, but the negative or the electrons can. So the electrons are going to be repelled by the negative rod, and they're going to move to the other side of the sphere. So let's see that happen. The rod comes over this way, and the electrons pile up on this side of the sphere. They're not touching, but we have movement of electrons to one side. To show what this looks like in real life, I'm going to put a video here of my coworker charging up a rod and bringing it close to an electroscope.
So I've got my rod charged up by rubbing it with fur, and as I bring it nearby, you can see I never had to touch it, but the 2 metal conductors have moved away from one another, and when I remove the rod, it collapses back down. That's called charging by induction. As long as I kept the ebonite rod in place, the 2 conductors stayed far apart from each other.
So what's going on in that video is that first the electroscope has the same amount of pluses and minuses, it's neutral. But then we bring the negatively charged rod close to it. And just like we saw with the gold sphere, these electrons are going to repel the electrons of the electroscope. So this repelling force, which I'm going to put with an arrow here, is going to cause the electrons to want to leave. And now they're going to end up on the needle down there. So let's see them move down and flow away from that top plate. Now if we look at the bottom, that needle has electrons built up on it, and the bar in the middle has electrons built up on it as well. Then the electrons are going to repel from each other, and it's going to bend the needle in that direction. And that shows us that there's a negative charge built up on that metal. Now at this point, the charge is just temporary. They've just moved down to that needle and are deflecting it, but if we pull the rod away, they would just go back up to the top plate. But next, look what happens if we touch the electroscope.
Just as we did before, and charge it by induction. And then while the rod is still in place, I've not touched the rod to the piece of metal, I'm going to take my finger and I'm going to touch this. And then I'm going to remove my finger and remove the rod. What do you notice? It looks like I've permanently charged this electroscope.
Now what we've done is we've created an escape path for those electrons. They want to get as far away from that rod as they can. So now we've attached what's called a ground. This finger is acting as a ground. This is a place for electrons to leave and go towards the ground or towards the Earth. We're going to mention ground quite a bit, and it's because the Earth acts like a huge electron sink. It's really, really big, has a whole bunch of neutrons and a whole bunch of electrons. And it can take a very large number of electrons and still remain neutral. You can dump charge into it and the Earth isn't going to become negative. It's got so many pluses and minuses, it's a very, very small effect. So it still stays overall neutral. Similar if you have a positive material and it takes some electrons from the Earth is still pretty much still neutral, so it can give a whole bunch of electrons away. So we will look at it as a kind of an infinite source of electrons or an infinite sink to dump electrons into. So now that we have that path where we can dump electrons, the electrons again are trying to get away, so they're going to get up and flow away from the system. We've given them an out and somewhere for them to leave to. So now other electrons are going to follow as well, and the other ones are going to redistribute, making the electroscope positively charged. So now when we take away the ground and we take away the rod, we have a positive electroscope remaining. And so it's got that positive bar and positive needle, and they repel each other to give us that reading. So now we have charged this electroscope by induction. When I first learned charging by induction, I was told this analogy of students in a classroom that really stuck in my head, and I'm hoping it does the same for you. So let's imagine this is a classroom and there's students all equally spread out and they're quite happy there. And they like to be equally spread out. They like their personal space. And everything seems fine there until all of a sudden a bear comes into their room. The students are shocked and they are terrified of the bear. So what do? They don't want to run towards the bear, they run away from the bear. So they all run to the farthest corner to get as far away as possible. Now that's good to move to the other side of the room, but what would be even better would be if they could get out of that room entirely. First, there was no way to get out. Now looking at the diagram, look at the top right and there is a door. Before it was closed, but now the door is open. If there's a way to get out of that room, students are going to leave that room to get away from the bear. So just like electrons leaving this room, students are leaving the room. Now, if the bear goes away, we have much fewer students remaining or fewer electrons. And again, they like their personal space, so they're going to spread back out. They've got tons of room and they are now happy again, but there's less of them. This is the same idea as what happened with the sphere and the rod. The rod was the bear, and when it came close, all the electrons moved to the other side of the sphere. And then when we attached a ground, that was like an escape route or opening a door, so lots of electrons left through that door. Then when we removed the bear or removed the rod, then the electrons were free to spread back out, but we had less of them. So now we have a positively charged electroscope or a more empty classroom. And that's it for today's lesson. So just to conclude, we have charging by friction when surfaces rub against one another and the electrons move from one surface to another. We have charging by conduction when a charged object contacts another one and electrons flow to balance out the charge. And lastly, we have charging by induction, which is where a charge is brought near to an object, electrons move to create a temporary charge, but then when it's connected to a ground, electrons are going to flow and we will create a charged object once the ground is removed. In the practice questions, you'll see lots of different scenarios with induction involving both negative and positive charges, so just use the concepts in this video to apply it to those new scenarios. I hope that gave you a good understanding of charging in those three ways. Thank you for watching this video, and I'll see you in the next one.